Hi, we've been talking about 5.2 and the Riemann sums, and we figured out that if we have the limit as n goes to infinity, the sum from k equals 1 to n of f at ck times delta xk, then that's going to be the integral from a to b of f of x dx. So we're taking this Riemann sum and taking the limit of it as we make more and more rectangles, or remember we also wrote it as our delta x goes to 0. And once we have all these more and more rectangles, we end up with this integral, which gives us the exact area under a curve. Now I wanted to show you if we take the curve y equals x, and we go from -1 to 1. If we take this area and we just do the integral from -1 to 1 of x dx, then we're going to get 0. Because this area is negative, remember we talked about before, and this area is positive, and they are the same, right? Area here is 1/2 base times height, and the area here is 1/2 base times height. And so this area is -1/2, and this area is 1/2. Add them together, and you get 0. Now, if we wanted to know our net area, our total area, we could take the integral from -1 to 0, and then change the sign of it, and add it to our area from 0 to 1, and then we would get the net area, because here we would have negative times -1/2 plus 1/2, and that would give us 1. So that would give us our total area of the whole part, but we have to break it up or we're not going to get the whole area. So make sure you understand what they're asking for. If they want to know what the area is and it crosses the x-axis, you need to make sure if it's total area that you're looking for, the area. Let me see if I can remember how your book words it exactly. Let's see. I think they just call it net area. So anyway, the net area. And area is usually positive, so you take care of that anyway. But that tells you that you have to pay attention to that. Now, if we want to be able to do other functions, like say we have the function y equals x, or 1 over x. If I can graph it properly here. So y equals 1 over x looks like this. And if we wanted the area under the curve for this one here, from here to here, you can use discontinuous functions, even though it doesn't look like you should be able to. But you have to break it up. So we would have to go from -1 to 0 and from 0 to 1 to be able to find that. So discontinuous and integrable functions, you have to use your graph to break it up into intervals. Now, just like on your calculator, with derivatives, on your calculator you can do derivative or integrals. So let's say we want to find the area enclosed between the x-axis and the graph of y equals x squared e to the -x from -1 to 3. So let's look at what that looks like. So we put it into our y equals, and then we can graph it. Now we just want to look from -1 to 3, so let's alter our window. So we go from -2 to 4, let's say, and it looked like it was pretty close. It was pretty close to the x-axis, so let's put that from -5 to 5 so that we can see the graph there a little bit better. And it's going to spaz out on me again. Sorry, guys. So you should have a graph. There you go. All right, so from -1 to 3, we want this area under the curve from -1 to 3. So how can we figure that out? Well, we've got what we're looking for is the integral from -1 to 3. It doesn't cross the axis, so we're good there. E to the x, or x squared e to the negative x dx. This is what we're looking for. Now what we can do is type this in our calculator. So go back to the home screen and then hit math, and it's number 9. It says fnint, or something like that. And then we're putting in our limits of integration, -1, and then arrow over to 3, and arrow over again. We want x squared e to the negative x, where our integral, our variable of integration is x. So basically we just typed this in to the calculator, and we hit enter, and we get 1.872 is our area there. So you can do this on the calculator. Some calculators call it fnint, and some it's fnint, and that just depends on how they do it. So you can work this on the calculator. Now we are going to figure out how to do these by hand, but it's just like derivatives. We can do them by hand and we can do them in the calculator, and you can use either one, but at the same time there are some that you're going to need to use the calculator because it's really complicated, and we'll do some like that. And then there are some where you won't be allowed to use the calculator because they're not that big of a deal. So keep that in mind. You can use this just like you could with the derivatives, but don't get too dependent on it because you also have to be able to do some of these by hand, which we will start working on with the next section. So, integrals, what you need to remember from 5.2. From 5.2, you need to remember that the limit as n goes to infinity of the Riemann sum, if I could draw a sigma, that would help. K equals 1 to n. So as we get infinitely many rectangles, or if our delta x goes to 0, then that's the same thing as the integral from a to b of f of x dx. Okay, this is the limit definition of an integral, and you need to know it. The limit of the Riemann sum is the integral. You need to understand that the integral is the area under the curve, and the definite integral, you will get a number value for your answer every time. Okay, we will do indefinite integrals later where we're just getting functions. That's different. Right now what we're looking for is the definite integral, which is just a number. So make sure you've read all of 5.2 and watched both videos and got some notes so that we can go over this in class.